Hello everyone, my name is Keyi. I'm from the Smart Construction Research Group at New York University of Dhabi. Next, I'm going to present our work about genetic-based temporary elevator planning from a spatial-temporal perspective. So let's get started. The temporary elevator is a piece of equipment that transports construction resources. With the increase in the construction of high-rise projects, the vertical transportation of resources is becoming significant. Effective temporary elevator planning is what the project team cares about. It plays an important role in transportation capacity and cost, and is a critical element for the successful completion of high-rise projects. The transportation demand for temporary elevators varies frequently and significantly. To its effect, temporary elevator planning should be adjusted accordingly to meet actual transportation demands. In other words, the number and the type of temporary elevators serving different days and floors should be dynamic and not static. However, existing temporary elevator planning is rarely conducted from a spatial-temporal perspective. To be specific, although the service floor of temporary elevators has been taken into account, the service day of temporary elevators is scarcely involved. Thus, temporary elevator planning loses an opportunity to be further optimized. Moreover, the installation and the dismantlement dates of temporary elevators cannot be determined reasonably when there are multiple ones in a project. To address these shortcomings, this research investigates how to configure temporary elevators to serve specific days and floors to satisfy transportation demands using a genetic algorithm. The objective of the model is to minimize the total cost of configured temporary elevators while satisfying the limit of transportation time. And it is expressed in equations 1, 2, 3. The total cost of temporary elevators consists of fixed and variable costs. The fixed cost includes the installation and dismantlement costs of each temporary elevators. The variable cost includes the rental, maintenance, and the personnel costs of each temporary elevator. The transportation time on one day is determined by the maximum transportation time among all temporary elevators, and the transportation time limit on one day is determined by the project team. The transportation time of one task is divided into three parts, namely the cab motion time, the cab door operation time, and the transfer time of works, as expressed in equation 4. If the distance of a segment is not less than the distance required for cab of a temporary elevator to perform a complete acceleration and deceleration process, the cab motion time is determined by the first fraction of equation 5, otherwise by the second fraction. To facilitate model optimization, the 1-type and the 2-type chromosomes are designed as illustrated in the figure. In the 1-type chromosome, the information for each temporary elevator consists of 2 parts with 3 genes, and they are encoded in real-time numbers. The first part with 1 gene represents the type of temporary elevators, numbered according to the specifications such as lifting height, loading capacity, and the rotated speed. If the number is 0, like in the case of temporary elevator 2 in the figure, it means that there is no temporary elevator. And the service period in the one-type chromosome is ignored, although it is displayed. Meanwhile, the service floors on each day in the two-type chromosome are excluded. The second part with two genes represents the start and end dates of the service period of temporary elevators. The gene with one smaller number represents the start date. And if the two genes are equal, there is only one day in the service period. As shown in the figure, the service period of temporary elevator 1 is from days 1 to 13.7, and that of temporary elevator 3 is from days 18 to 15.3. It should be noted that the number of temporary elevators is not fixed, and the one-type chromosome and can be expanded as needed. In the two-type chromosome, the information for available temporary elevators consists of genes representing the service floors on each day, and they are encoded in binary. In the configuration of a temporary elevator is a dual cape, like in the case of temporary elevator 1 in the figure. The service floor of each cape is represented respectively. The gene with 1 represents that the service floor of the cape includes the corresponding floor, otherwise does not. As shown in the figure, on day 13.2, the service floor of cape 1 of temporary elevator 1 includes floors 2 and 5. That of cape 2 of temporary elevator 1 includes floors 2 and 6, and that of cape 1 of temporary elevator 3 includes floor 5. To exclude inherently invisible one-type and two-type chromosomes, the one-type and the two-type criteria are formulated respectively. The one-type criteria are divided into 4 categories, namely temporary elevator number, service day, lifting height, the transportation rule. For example, the category service day means that a service day is covered by at least one available temporary elevator. As shown in the yellow part, the service period of temporary elevator 1 is from days 13.7 to 15, and that of temporary elevator 3 is from days 1 to 28. In this case, days 29 to 36 cannot be covered, so its chromosome is invisible. The two-type criteria are divided into 3 categories, namely lifting height, service day, and transportation rule. For example, the category lifting height means that the lifting height of a temporary elevator cape is not known than the height of the floor it serves. As shown in the red part, the lifting height of cape 2 of temporary elevator 1 reaches up to floor 2, and it serves floor 3. In this case, floor 3 cannot be served by cape 2 of temporary elevator 1, so its chromosome is invisible. To test the proposed model, a 36-story high-rise project with a construction duration of 411 days served by 2 types of temporary elevators was used. The details of initial and optimized solutions for the service period of temporary elevators are listed in the left table. In the initial solution, temporary elevator 1 with type 1 and the temporary elevator 2 with type 2 serve all days, while in the optimized solution, temporary elevator 1 with type 1 serves days 1 to 341, and the temporary elevator 2 with type 2 serves days 333 to 411. The right table lists the partial details of the initial and the optimized solutions for the service floor of temporary elevators. For example, on day 339, all caps of temporary elevators 1 and 2 serve all the floors in the initial solution, while in the optimized solution, caps 1 and 2 of the temporary elevator 1 serve floors 36 and 31 respectively, and the caps 1 and 2 of temporary elevator 2 serve floors 31 and 13 respectively. The details of the initial and optimized solution for the cost of temporary elevators are listed in the above table. Compared to the initial solution, the total cost of the optimized solution is reduced about 341,000, which accounts for about 37% of the initial solution. The transportation time of the initial and the optimized solutions on each day is shown in the below figure. Their maximum transportation times are both less than the 90-minute transportation time limit. Compared to the initial solution, the temporary elevators in the optimized solution are more fully utilized within the transportation limit. In its research, we can have the following conclusions. First, multiple planning objects, including service dates and floors, are integrated into one planning model, which solves the limitation that service dates and floors are planned separately, resulting in a further reduction in the cost of temporary elevators. Meanwhile, when there exist multiple temporary elevators in a project, the installation and the dismantlement dates of temporary elevators can be determined with evidence to support the decision-making process of the project team. In future work, the integration of mathematical programming into the spatial-temporal planning model of temporary elevators will be investigated, and the computational performance of mathematical programming versus Meta-Heuristic algorithms will be compared. That's all my presentation. Thanks for your attention.